Is this on? Hello? I guess you can hear me. Can you hear me in the back? The people reading their email? Great, thank you. So Frank and I are going to have to go like back and forth. We'll try to remember, because they can't hear you if you don't talk into here. So we, basically this talk is about best practices, and there's only 40 minutes, so we just picked three ideas. We are actually theoretically working on a book called Effective Scala to capture that, because after 10 years of Scala, we've both been using Scala for 10 years. And I think the community has been using Scala for many years, and some ideas have emerged, so we were trying to capture them. So we wanted to give a couple today, so let's just switch all. Actually, why don't you go on this side?
Yeah, I'll go on this side. I'm going to try not to talk. Sorry. So we only have 40 minutes, so we're only going to give you like a synopsis of what we're trying to talk about in our book. But, I've been doing Scala for over 10 years now. I think we started at 2.8. And while Bill did the Scala test tool, which so many people use, I actually went ahead and started a company, and we have a pretty long and large code base that uses Scala. Like I said, it evolved from 2.8, and now we're on 2.14, I think, right now, and 2.12 now. So basically, we try to keep up to date. But what's interesting about that is that when I started out, we started from a Java background. Most of our developers had Java backgrounds, and now over 8, 9, 10 years, we evolved this code base. And what we noticed was that Scala is really an unopinionated language. You could do things in so many different ways in Scala, and when programmers come to the code base, they often wonder, well, what's the best way to do certain things? In other languages, like in Java or Python, other languages, you probably don't have so much diversity in terms of how you can accomplish pretty much the same tasks. So on the one hand, you could program in Scala as if it was, quote-unquote, a verse Haskel on a JVM, and I've heard that being said as one of the possible ways to think about Scala. And that certainly is a very valid approach, and I like some of that work. It's really interesting, and it's definitely a way to program in Scala. The other way, on the other hand, and a lot of people who come to Scala from Java, they program initially as if they were basically writing Java code with Scala syntax, without the semicolons. But what's interesting is that I heard Martin say this several times, that Scala is really about a third way. It's a functional, object-oriented language, and I often wondered, what does that mean? And when you apply it to actual daily work in terms of working on a code base, what would it look like? So this talk really is about this third way, which we think, at least that's our opinion, that it's probably a really effective way to work with Scala. So. Okay.
So I'm going to slide over here. We are opinionated, and Effective Scala is supposed to be opinionated. And so what our opinion is that the third way is the best for most projects. And what Better Java is really useful for is people who are just getting started. They're coming from a different language. Most of them are imperative. Most of the mainstream popular languages do things in a very imperative way. And you can just do that in Scala. And I think that's actually a good thing to get started. Just get stuff done in Scala the way you're familiar with, and over time you will learn more idiomatic functional ways or more idiomatic Scala ways of doing things, and that's actually helps people get into Scala. I've also seen a very hardcore functional style work great in practice in real companies, but the thing that has always been present is a strong leader at the top that sort of makes sure everybody understands those abstractions and sort of decides which ones to use, maybe which ones not to use, and makes sure everybody's going in the same direction. What I've also seen more often is that people, most projects are more like this functional, object-oriented, but not necessarily Haskell emulation approach style, and most people on the team are doing that, but there's one or two really passionate Haskell people who do this other way off to the side, and then if they leave, no one else can understand that code. So what's important is that everybody's going in the same direction. All these ways, I mean, Scala is unopinionated, and these different ways work, but it's not, and I want to say in the community, it's really exciting that there's these different ideas and people trying different things and going different directions and coming back and talking to each other. But in a single project, that's actually not the right place for it, we think. You should have one way of doing it in the project. And the management has to sort of make sure people are going in the same direction.
Yes, so in our book, we're planning to come up with about 50 guidelines about what has proven to be effective Scala programming, at least in our opinion. But here we're just going to give you 3 guidelines. So the first guideline really is that even though Scala is really unopinionated, and precisely because it is unopinionated, when you start a project, you should form a project opinion. You should decide which way you're going to go with that particular project, and then you should try to stick with that throughout the project as much as possible, and for the whole team. And so that's our first guideline.
Okay. So this, I don't know if Jamie Allen's here today. He might be at the conference, but he actually came up with this. He called it the he taught it to me in a class. He drew it on the board. He said, this is the mutability matrix of pain. He's very strong when he says that, and I thought that was a little bit harsh. So I rebranded it the immutability matrix of pleasure. So what this is an example of Scala is unopinionated, but we should be opinionated. So what Scala has is 2 kinds of variables, vals and vars. Vals can be initialized but not reassigned. They're like final in Java. Vars can be reassigned like regular variables in Java. And then objects can either be mutable or immutable. An immutable object, once it's initialized, you can't observe it changing state. Maybe it has a lazy val and that mutates later or whatever, but from the outside it's referentially transparent. It's immutable. Mutable objects, actually just the whole point of them is you can change them over time, right? So actually, we can actually take a vote here. I think this is San Francisco. So okay, in your heads, we don't have to take a vote. What do you think is the best, think about where you think is the happiest place to be.
Most pleasurable.
The most pleasurable place to be, not the least painful place, but the most happiest place. Okay, Frank, what do you think?
Well, I don't know what you mean by pleasure, but the most boring place is to be over there, in a sense that it's very predictable, right? So you have basically a val pointing to an immutable data structure, so you pretty much could predict what's going to happen in your program. Even if you have a concurrent program or single-threaded or actors or whatnot, futures, if you're there, most likely you'll be happy if you can stay there. Now, you may sometimes not want to stay there, and again, Scala gives you all these different options. You could do whichever you want out of these 4 options. So if you cannot stay there or you don't want to stay there, then which one would be the second happiest place? What do you think would be
the second?
like
we can take a vote now. The second,
yeah, we could
this
take
is
a
the
vote
hard
now.
one.
So who would vote
one.
for this as a second happiest place?
Okay, I've
So
got a few
here
hands.
we have a
I
var
would
pointing
say
to an immutable data structure, and
I
here
think
we
that's
have a val pointing to
36.7% approximately. How about this one? I have,
So it's a val
okay,
pointing
that's
to mutable data structure.
22.3%. How about this guy right here? 0%, 1%. All right.
But this is the most exciting
2%.
place. You guys
I feel like I'm
missed
at
out
an
on all.
auction.
We missed
How much
out
would
on
you pay for this quadrant? So, okay, we're going to reveal what we
Yeah.
think. It's that guy.
So why did you think
Oh,
is the...
well, actually, I think these 2 are quite close together. This one and this quadrant and that one, this one. But the reason this ended up number 2 is because on the JVM you have multiple threads, and it's easy to close over an object and pass it to a method that may actually pass it to another thread. So it's a little bit safer to use a var pointing to an immutable, because if you close over a mutable object, then you could share it with a thread, and its mutable state being shared by multiple threads without synchronization, and that could be a concurrency bug. Especially if you're doing Akka programming or concurrent programming, that's true. So what about the third one?
Yeah,
I
well,
think
the third
we gotta
one,
switch here.
I would pick this quadrant here. It's less happy than this one. So why would you want to do this? So why would you want to do this? So here we have a val pointing to mutable data structure. Well, one reason I can think of doing this is for performance. I mean, sometimes algorithms are expressed really best in the mutable data structure, possibly. And it's still better to have a val, like an immutable reference pointing to it. But this probably would be the third happiest place.
Yeah, and the last one is this guy. So here, what I think is interesting is that this is the regular way of doing things in Java. It's like the normal way. And in Scala, I actually don't recall ever seeing a var pointing to a mutable in code. I haven't done it myself because there was never a reason to. If I have a mutable object, I hold it from a val. So it's, I think, an example of how Scala, not the syntax or the grammar of the language has an opinion. In Scala syntax, it's just as easy to do any of these four combinations syntactically. But there's an opinion of the community, and also, you know, like Scala's actually trying to promote that people should do things more functionally, which is val immutable, and so that's essentially what I think that shows. So.
It just shows the diversity, but I mean, when people come to Scala first, they may start doing this, right? And I think the journey of a Scala programmer is probably going towards that direction. Yeah. But then again, sometimes what we're kind of saying is that it's okay to do those two things as well. Okay. Scala doesn't let you do all of those things. So our second guideline, number 2, is that, you know, Scala is a functional object-oriented language. So I think when you form a project opinion, it's probably really important to know for that particular project, what are the benefits of OOP and what are the benefits of functional programming? Okay,
so I'll start with functional programming. I think the big benefit of functional programming as you scale up is that it helps you reason about code because of referential transparency, which means that a pure function, if you pass it some data, it crunches on that data, but it doesn't have any kind of effect that you have to keep track of off to the side. It just returns something, and everything it does is sort of embodied in that result. And if you pass it the same thing, you always get the same thing back. So you can actually conceptually, in your head, replace the function call with the result, and you're fine. You don't have to remember something in your head that function did off to the side. And in the small, you can reason about imperative code, but in the large, this really helps you understand code and helps us build things that are more complicated. So I wanted to give you an example of that in the small, imperative code is actually easy to reason about. It's not just that imperative code is always hard to reason about. So this is the implementation of the exists method in list. And if the list holds onto immutable objects, if its elements are all immutable, and the function here is pure, then when you call exists, it's going to return a Boolean. It will always return the same Boolean given the same function. And that makes it referentially transparent from the outside, but on the inside it's actually doing side effects because there's a var there and it's holding on to an immutable. So that's the upper right quadrant of that mutability matrix or immutability matrix. And then it actually reassigns the var, that's a mutation, and then it actually returns out of the middle. I mean, this really looks like Java code. But on the outside, it's pure. Right, so that's like if you can encapsulate keep your mutation in little pieces, people can reason about the code on the inside and they can reason about it on the outside because it's FPO. So,
I mean, clearly this shows that in the small you could keep track of side effects, like a little loop. Everybody could see in 2 seconds what it does, and I don't think you can make a lot of mistakes about it. And even if you do, it's kind of constrained into this function. But the real problem with mutable state, obviously, is in the large. And what's the problem with that is that you have to keep it in your head. You have to track how you mutate the state. And in my opinion, that's really the problem. So, I mean, even going back to something like C programming days, basically mutating the heap is essentially this problem, right? We're trying to keep in our head how we mutated the state of the heap. So if we allocate, for example, let's say, 4 bytes there, and we keep allocating some memory, and then we allocate it now an additional 3 bytes. So let's try to free up some memory. So these tabs, we have to keep in our head, right? So this is the whole reason why automatic garbage collection became so popular and kind of won out, is because it means that you no longer have to keep this in your head. However, we still mutate this data structure, it's just we don't have to track it. So this is the reason I think why mutable state is difficult. Not in the small, and I would argue in the small is probably okay, but in the large, you have problems when you have to track it and you forget, and now suddenly your program crashes because of a memory leak, or because, you basically just like, you free the gain, your program's going to crash with a core lump.
Yeah, like malloc is not a pure function, right? Malloc has a side effect. It does return something, but you have to remember that you allocated that so that you have to remember, because you have to remember to free it later. I also have to remember, free is also not a pure function. It has a side effect. It mutates this heap, saying, okay, this is now available. I just have to remember that I did that so that I don't free P2 twice, because that's when it corrupts the heap. The heap never checked for that. It just let you do it, and then it would just corrupt itself, and then sometime later the program would crash. The other way is if you forget to free something, eventually the program crashes because it runs out of memory, right? So that's one example, I think, of like in the large, imperative code is hard to reason about. Another one is this thing we've been struggling with for a long time now in the Java land, which is it's hard to get concurrent programs right. And I later realized that that's because this is a mutable data structure. This is what logically exists for every object on the JVM. It's called the monitor. It's a fancy mutex with some extra features. Essentially, because it takes memory, they don't create them until they're needed. So objects that don't actually have synchronized methods, you don't get one of these. But when someone calls a synchronized method, if it doesn't exist already, they're going to create this data structure. And the thread that enters the synchronized block, it actually goes into this wait set, and that mutates this. So the wait set, this data structure now knows that thread's sitting there. And then if no one's in this center room, that's like the room only one thread at a time can be in, then that thread can go in there. That's a mutation. It says, well, now this thread's in here. And if it either completes and just returns or exits out the end of the synchronized section, then it goes out the bottom door. That's a mutation. Now the room's empty, right? If it blows up with an exception, also that goes out the bottom door and that mutates the thing. If there's a thread inside there that says wait, then actually the thread will be put over here into the wait set. That's a mutation. And there they want to, they need to wait until someone fills a buffer, or another thread comes in and fills a buffer so they can empty it or whatever, right? So when another thread does that, they'll say notify. Well, that'll change these orange ones and they'll all go to green. Well, notify has one of them go down there. Notify all has all of them go down there. That's a mutation. And now when this room becomes available, the green ones and the yellow ones will compete, right? So if a green one goes back, another mutation. So it's mutation, mutation, mutation. And this is every time I enter a synchronized method, it's actually having that side effect that I have to keep track of. And in the small, you can get it right. I mean, you can make a little producer-consumer class with synchronized and wait and notify and get it working. It's just when the large, you end up, 2 weeks after you deploy to production, you get a deadlock. And because you screwed something up, it's really hard to keep track of it. So it's another example, I think, a really good example of, in the large, side effects are hard to reason about. Impure functions are hard to reason about.
Yeah, but in the small, they actually sometimes work. So interestingly enough, object-oriented programming, originally, it was also kind of designed to deal with large-scale complexity, right? You have a large, complex problem domain, and the classic O design essentially breaks down that problem domain into classes and objects, which in some way model that domain. And secondarily, they would allow you to bundle data that's related together into the state of an object. So the whole purpose of this was originally, I think, to help design complex systems and to manage the data, the state associated with those objects. So here's an example that anyone could pretty much instantly understand. This is an object-oriented API. This is not Scala's map. It's actually a Google's map API. This is, in fact, a facade that we created for the Google Maps API, one of our projects. And what's interesting about it is that everyone can understand this instantly, what this code does. The reason for that is a couple. First of all the function names clearly designate some operation that in your head, you already know what the map does. And this just corresponds exactly what you would expect. For example, if you want to set the map to a street view, you know what a street view is if you use Google Maps. It does it exactly what it says. The methods names are not some kind of an abstract operation. They don't define some abstraction. They define exactly what that object is you think will do. And that's probably one reason why so many hundreds of thousands of people could use this API instantly. The other interesting thing about this is that this object, this map object, actually has state. It contains the state of that map if it's displayed in your browser. And for example, you can mutate that state. This returns unit. And it mutates what type of view you present. For example, a satellite view or a street view. So it manages state. It actually is a mutable object. And the point I want to make here is that this is actually very easy to reason about for a developer, right? Because you know exactly what it's doing. It encapsulates the data, and it bundles those functions together with the data. So this is really one example as when object-oriented programming can help you deal with complexity, because the programmer understands exactly what that code does. And that's one reason why it's helpful.
Yeah, I'm not as good a marketing person as Frank, because now I know you really all want to use object-oriented programming because you'll know exactly what it means by looking. And it is actually an abstraction. It's a domain abstraction. It's not a mathematical abstraction. I think that's the kind of the thing that I think actually OO decomposition usually does in terms of domains. I mean, when you see map, you may think, well, you may think it's like a collection of key value pairs, but when you see get street view and it's from Google Maps, you're going to say, oh, I'll bet you that method returns, basically that kind of thing helps people reason about code. Domain naming, and that's what OO, you know, the nouns of class names and verbs of method names can really help people understand.
I would say it makes
yeah.
the code. I would say it makes the code accessible to programmers.
Yeah.
So that's the OO part of it, basically.
Okay. So let's go to the next one. Okay, so I wanted to show a example of another example where you have side effects in the small. And what this is the implementation of List.makestring. And it's, you know, it takes three strings, the start string, the separated string, and an end string, and it's on list. So what is supposed to happen is it's supposed to return an immutable string that has, you know, the start string at the beginning, the end string at the end, and then, you know, .toString and all the elements separated by sep. And the way it does is it creates a string. It actually uses this helper method called addString, and that takes a string builder that could have some state in it already, but we create an empty one, and we just pass these three strings in there. And then it returns the same string builder that has been mutated. That's what addString does. It's a helper string inside list. And then you convert it back to an immutable on the way out. So this is, again, pure from the outside, as long as list has got immutable data in it, which usually that's what we do. When I call makeString and pass in the same strings as input, I'll get the same string as output. So it's referentially transparent from the outside. But on the inside, it's a lot of mutation going on. But I wanted to show you that inside the addString method, the string builder coming in is referenced from a parameter named b, and that is a val because parameters in Scala cannot be reassigned. So this is an example of the third quadrant down at the bottom left. We've got a val holding onto a mutable object, and the reason it's being done here is because that's faster. I could do this all with just string concatenation, and I would get a bunch of garbage strings, and everybody does it this way if it has to be fast, because it is faster. Like sometimes the fastest algorithm that we can figure out is with mutating state, right? So when you have a reason to do that, OO is a great way to do it. It's nice to have that state encapsulated inside the string builder class.
But note that the string builder is returned from the helper function, but it's not returned from the the string itself is returned from the functions. In other words, the entire mutable state is considered inside a particular function. Yeah, the make string.
Here, I'll do this.
So our third and final guideline is kind of to summarize what we're trying to say here, which is basically that when you develop a larger Scala application, what you're finding helpful is to think about it in this way. If you have I/O coming into your app, you should try to confine that region to some well-defined part of your program. And in that region, you probably will be interacting with mutable APIs, with Java APIs, with input streams or whatnot, but that region should be well-defined in your program. Inside your program, like in that makeString method, you would see that there's also a mutable state. In that case, you should try to confine that to just one thread of execution, and from the outside, that region should be functional. Everything else in your Scala program, you should stay pure as much as possible. So we call this outside region the wilderness, because basically you're interacting with the wild. It's essentially whatever goes there, you just have to interact with the world from your program. And very often the best way to do that is to use thread synchronize, to do whatever you can to manage your I/O there. And very often, again, you may have to interact with existing Java APIs if you exist in the Java ecosystem. In your pure region of your code, you should really stay referentially transparent completely. That would really help you reason about your code. And most of your Scala program should be in that region. And then in the confined regions, confined because it will be confined to one thread of execution, you can use mutable state. We think it's okay to do that. And it's partly for performance, but it's also partly if you need to use existing Java APIs that are mutable and that are not functional in any way. That would be your confined region.
Okay. So one way to think about it is as a call stack. So this is a picture of a call stack that grows downwards. So like the thread starts at the top, and each one of these rectangles is a stack frame that's been pushed onto the stack. when a method is called. And so at the top is where, the wilderness region, I might be doing I/O, I might be calling into Java libraries that are useful to me. But once I hit a pure function, everything actually has to be pure all the way down, because otherwise it wouldn't be pure. I mean, if there's something down here that isn't pure, then I'm not pure up here, right? So once you hit it, you kind of have to. But what we try to show in this picture is that hopefully most of your code is pure, because that helps you reason about code in the large. But down here, there's the hot spot. A lot of times what you're going to do is call into the Scala libraries, and like List.exists, you might call that a List.makestring, and that's actually doing mutation on the inside, but it's confined to one thread. Those mutable objects are not synchronized, like string builder is not synchronized, so it has to be used by one thread. But it's done just it's a local mutable object, local to that thread, and so that is fast. So whether you do that yourself or not, it's sort of happening down at the hot spot, the part of your code that has to be fast. If you have a performance problem, then you might need to actually do that yourself. Like you find, oh, this method is taking too long, so let me use a mutable object instead. But if on the outside it's still pure, I mean, if it isn't pure, then boom, the wilderness went all the way down here, because it's not pure anymore on the outside. So if it's pure on the outside, then you can do all the mutation you want locally, and in Scala you can just write it. You can write a while loop with a var.
Yeah, and I think that that's basically our guideline, is you should always try to think of the boundaries between these different regions very clearly. So here's one example. This is actually something that our code does in our enterprise app. It's basically what we're trying to do here is to have some input, some data, and an output stream, and we try to create a PDF document, merging this data into some format, and then return this PDF document in the output stream. So this is a really common enterprise task, probably. And so basically we get this I/O request through some kind of a socket, or it's an HTTP request or something like that. That's going to be a lot of mutable data structures there. If it's a servlet, you're going to have a servlet request, which is completely mutable. It's a Java class. It's really what you have to deal with, though. This is something that many enterprise apps would have to deal with. But once we get this request, we enter this pure region of our program. So this function here takes an immutable data structure here, which is a PDF request in this case, and it returns an immutable data structure as well, an immutable object, which is PDF data. So this entire region here will be referentially transparent to this region here. So given the same input, it will always return the same output. And then in this region, we would do basically pure functional data transformations, for example, formatting this PDF data, filtering it, or doing whatever computations we need to arrive at the data that we would need to create this PDF given the input. Now, to generate the actual PDF, we happen to use a Java library, which is in our case iText, which is a totally imperative library. It keeps some object and it keeps mutating that object.
Like string builder.
Yeah, like string builder, basically step by step by step. I have to say it's a very effective library. It lets you basically manipulate PDF extremely powerfully. So we confine the use of this API into this confined region. Again, even this function takes an immutable data structure, and it returns an immutable data as well. But inside this function, we use mutable data. In our case, it's primarily because we're using a very, very imperative mutable Java API.
Yeah, in that case, it's not for performance. It's just there was a mutable library that he wanted to use. And as long as he used it, built a PDF, but then he converts it to like .toString on string builder. He converts it and returns a vector of byte, which is immutable. So another way to think about it is with a Venn diagram. And this is just, the spaces here are like your code base, your code space. So this is like all of your code that you could think of as placing into these three categories, and you hope that the kind of yellowish category in the center is the biggest one. The purple category here, the confined regions, that's there if you're calling into the Scala API, but you may not do that yourself. But for example, that app, Frank did that. His calls to iText are in that purple region, right? And then the wilderness is on the outside, and that can be greater or smaller. And that's sort of one of the things we wanted to say was that it's okay if whatever fits your team and your project is actually fine. I mean, you want to make this as big as possible, the pure region. It's okay on the inside to use some mutation for performance or for using a library. It's okay if on the outside you make it razor thin and you use IO-monad. That's okay if the whole team is kind of up to speed on that. But it's also okay if you just actually keep it small, and if it's small, you can get the program to work and it's fine, right? So it could be smaller or bigger or whatever. But that to me is not, I mean, we want to compare it with some other things. This is sort of Scala's pattern for application
so
structure.
try to give it a name. Like I just think this kind of happens in everyone's code base. Like, so we try to give it a name. And Bill and I like to eat bagels, so we just thought it looked kind of like a bagel.
Well, how does it look like a bagel?
Well, because it has a round center, but the round center in a bagel is empty, so it didn't quite fit. This was very good part of the bagel, right? But then we kind of like to stay in that part, but it didn't quite work. So we thought of Saturn perhaps, but the Saturn here is kind of empty, so that didn't quite work either. And then we went to this conference.
We gave a similar talk in Berlin. That was Scala Days this year. And in Berlin, we discovered the Berliner. That's a jelly-filled donut. And it's like, I was eating this for breakfast. I'm like, oh my God, that's actually the perfect shape, because it's not empty on the inside, and it's kind of gooey, like mutable. So
it tastes really good. The jelly part, I have to say, is probably
and it tastes good because it's fast. So we called it the Berliner pattern. But that's, I think, and notice the other thing I liked about it is the outside was very thin, right? Because we really want to, that's like idealistic, right? We want to make that as small as possible.
Especially because sugar is not that good for you, so you should keep it thin.
Okay, yeah, it's usually powdered sugar in the Berliner.
Well, right.
Okay.
So if you don't do this, then you can also do this with Scala, right? You can basically try to eliminate the inside and just keep everything purely referentially transparent. Basically, just use pure transformations. In Java, Scala allows you to do this as well. It's kind of like the reverse Haskel on a JVM.
One more little comment about this one. So actually, I think the wilderness part is too thick in this diagram. It would actually be razor thin, conceptually, but really, if you think of like your main method being included in that, there's got to be some I/O somewhere, so that it actually does happen. And there's really the purple in the center too, because if they're going to be calling into the Scala API, they're going to call List.exists. It's actually doing mutation on the inside, but what you're trying to do in Haskell is just everything's pure everywhere, right?
And this works in Scala, so you could totally do this. It's important to have a project opinion. That goes back to Guideline 1. If that's what you're going to do, then this should be a decision, and probably you should try to stick to it. Otherwise, everybody knows this. So what would a better Java in Scala look like? Well, we'd think it would look something like this, and this was actually from last night. We had dinner, and we were looking at this clam chowder soup, so we figured that people in San Francisco...
It's in a sourdough bread bowl.
Bread bowl. It would actually kind of fit this, right? So here, we have a really gooey inside, right? And then we don't know what's happening here. A lot of leaking abstractions.
That's a concurrency bug, actually.
It's a lot of leaking abstractions there. But
seen in the...
So it basically would look something like this. So basically you have mutable state all over the place, and then you have this I/O where you essentially perform I/O. So this is basically Java, right? There's no clear delineation. And the point we're trying to make is that this is probably not very good in Scala, but some programs are like that. Probably you shouldn't choose this as your project opinion, but it works in Scala, so it's good to be aware of that.
One other thing I would add to that is that Java doesn't talk about pure functions in the Java community. We didn't talk about that much, but we did talk about making things easy to test. So like if you write your test first, a lot of times you'll end up with a pure function because that's easier to test. So I think that's sort of where it snuck in Scala, Java, I mean. But anyway. That's the pattern that we think is Scala's. That's what Scala is trying to. This is the opinion of what you should use Scala to do most of the time. So before we take questions, I wanted to just mention we don't have I don't think have we written the first word of the book.
No, not the first word yet, but...
So we did make a workshop just to try to flesh out the ideas. So this is all 2 days of best practice. So if you're interested in that, that's something. We just gave it earlier this week as a public one, and we'll do another public one in a few months, or we can come in-house. And then the other thing is our team is my company. We do consulting, so we're always looking for programmers. So if anybody's interested, come talk to me or email that email. And we are available if somebody needs help with Scala. We're just focused on Scala. And then I'm also a member of the advisory board, the Scala Center Advisory Board, and I represent the community. So I'm supposed to like know what you think and what your concerns are, and people don't ever complain to me. So I would like to invite you to come up to me at the conference and tell me what your concerns are, and I can relate them to the Scala board, the center. So thank you, and we are ready for Q&A.
Or complaints, right?
Or complaints, that's correct. Yes.
So I think if you can hear without the microphone.
Yeah, I'll repeat the, okay.
Okay, so the question is, all this pattern, all these three zones, does it lead to some sort of specific code organization patterns? Like, for example, do you isolate all the zones in different models, different packages, or do you mark them somehow? Or like, the motivation for the question is when a new developer comes to the project, they see the code and they will think something like, oh, this thing is mutable, I will change the immutable. So how do you suggest to them that this should be like this?
Yeah, that's a great question. I don't know if I need to repeat it, but I might need to repeat it for the, do I need to repeat it for the video?
Yes,
Anyway,
please.
I'll repeat it.
Yes, please, yeah.
Unfortunately, I forgot it by now, but no, it was essentially a great question, which I don't actually know the answer to, so I'm gonna let Frank answer it. Is there a way, like, you would organize the code to make it clear that this is this region, this is
Yeah.
that region, and that's the other region? So that's
Yeah,
a
so
great
I'll give you a
question.
couple of examples. I mean, we have seen this working with developers who come to our code base. So for example, leaking something out from here, if you return a mutable data structure, right away you leak some abstraction into this region, right? Because this can also mutate it. So right away, I would say in that case, you would need to return an immutable version of it. So that's just one example. So basically, the second thing I would say is that when I first like really try to do functional programming in Scala, like I really thought I was going to go all the way to like the Haskel style. I really kind of thought that that was an ideal to strive for. I really felt guilty using mutable data structures inside my functions. But then again, we didn't know what to do with all these Java APIs that are just super useful to use, and they're very imperative. And that's where I think this region comes in, that this has some value to it. So I would say it's a larger organizational principle. And however, when we use those APIs, we make it really, really clear that we're going to confine that to, as much as possible, to one thread of execution, and we're going to be functional from the outside of that function. So I think in code reviews, that's probably a good principle in generally speaking. And the second thing I have to say is that we don't use monads, or we try to keep this layer thin, but not super thin, because we just didn't see the payoff to keep it super thin. It could be, but not in our case.
I wanted to just say, I actually I can't think of how to make that clear in the code, but I'm gonna think about that. That's a good question. I don't either use, a lot of cats or Scala Z, but I'm very interested in it, and I think there's things for me that, I mean, one thing that I would like to get rid of is dependency injection. I hate that, and that would let me do that. So I think, I guess what we're trying to say is it's okay. It's actually, there's a lot of value there, but it's not like you're not done yet if you're not programming that way. Most people don't program that way, and if this part is actual just Java on the outside, that's actually fine. You still get the benefit of having mostly pure functions. So any other questions? Yes.
I mean, it's always.
Thank you.
The question is about the code sample, a Mac one, which looks a lot like a Java way of doing things. Like
Yes.
you got an interface and you got an implementation. So the question is, so do you have any clear separation between this way and, for instance, using type classes, and which one will you pick up in what case?
Okay, so I'll repeat the question. So this is very Java-ish. It's a mutable object, essentially. There's a set heading, right? Get heading, set heading. That's very Java-y. Excuse me. And it's wrapping a JavaScript
It's going to be
library,
a JavaScript
right?
API.
I'll let you switch.
Which interestingly is confined to one thread of execution with JavaScript. So it's a good example. It's mutable state, but it's confined to one thread just by virtue of the fact it's running in the browser. But
Yeah, I actually have an answer there.
yeah, sure, go ahead.
So yeah, so basically type classes versus this. When I think of this, this is kind of OO. So like inheritance hierarchies, I think everybody in OO, not just Scala, but learned that big inheritance hierarchies are hard. So we usually keep them pretty small. And when something cuts across these smaller inheritance hierarchies, that's a great use case for a type class, because it can be independent of it's another small inheritance hierarchy actually. So you have these two now, and so that's how I think of it. Is the OO way is, the inheritance way is good in the small. You can actually do big ones. Like Scala.exists is actually kind of like a big one. You know, you mix in these traits and you do trait linearization and super dot, you know, and all that stuff. But most of the time that just is too much, and you just have these little inheritance hierarchies. So things like how to order a type that cuts across lots of different inheritance hierarchies, then you can you would use a type class for that. So it's time for another question. We got okay. All right, yeah. Okay. Anybody have one more, or you also a complaint? We have time for one complaint. Anyway, yeah. Okay. Alrighty. Well, thank you very much for coming to our talk.
Thanks very much. Thanks a lot.